Okay, so now we're going to get started with chapter 2, which deals with molecular representations. And one of the big things, two of the major concepts you're going to take away from the beginning of this chapter are going to be the functional groups. So you have to memorize all of the functional groups because they never go away. The functional groups: alkene, alkyne, ester, alcohol, ether, amide, amine, etc. So you have to know the functional groups frontwards and backwards, and then also bond line structures. So bond line, which sometimes people call skeletal, but bond line structures. So you might have seen some bond line structures already in your chemistry journey to this point. For example, if you studied benzene in general chemistry and you saw a structure that looked like this, where it's just a bunch of lines on a page, okay, that is a bond line structure, okay, of benzene. And it's a representation of, you could represent this as a Lewis structure, but there's a reason why we use bond line structures. And I'm going to get into that today. But what are some structures you're familiar with? Well, you definitely know Lewis structures. We talked about those in chapter 1, the Lewis structure in detail. And Lewis structures are great because they show every single bond. They show every single lone pair. However, Lewis structures, as great as they are, they're really only useful for small molecules. And we like to use Lewis structures to determine molecular polarity, like I showed you in chapter 1. And so sometimes we'll partially condense a Lewis structure and come up with a partially condensed structure. And these are ones where we usually just condense the carbon-hydrogen bonds. Now, if you look at the structure that's shown here, you might say, well, that's not really true because they condensed this CH3 and then they condensed this CH3, but they didn't condense this carbon-hydrogen bond shown here. That's not condensed. Well, you're right, but remember, it says partially condensed, okay? So we condense some parts of it, but maybe this part wasn't condensed for a specific reason. Maybe somebody wants to show you this bond for, because maybe it helps demonstrate reactivity or something like that. But again, a lot of the bonds to hydrogens are eliminated in a partially condensed structure, so it saves you a little bit of time. Then condensed structures can be useful at times because they eliminate all single bonds in a condensed structure. So you see how in the molecule we have the two CH3s that I have circled in blue. And so what somebody did here is they said, well, I'll put those two CH3s in brackets, and then I'll put a subscript 2 outside of that bracket. So again, if I zoom in, you can see there's a bracket here and a bracket here, but this 2 denotes that there's two CH3 groups. Then we have our CH, and then we have our hydroxyl group. And then finally, molecular formulas. Well, obviously, you've used molecular formulas a lot in general chemistry. However, what's the problem with the molecular formula? If you have C3HO, well, the problem with that is that it might be something like CH3, CH2, CH2OH. That's one possibility for a way to connect those atoms. Or it could be CH3O, CH2, CH3, right? So what that means is that you have a whole host of isomers that could be represented by this molecular formula. So even though it provides the makeup of the compound, it doesn't tell you anything about the way the atoms are connected. So in terms of connectivity or structure, molecular formulas are useless, okay? They can be used for calculations, but they're not really useful when we're talking about structure. So with that in mind, let's see if we can draw a Lewis structure for these condensed structures that are shown here. So we have a couple of condensed structures. So what we're doing here is we're going from condensed to Lewis structures. So let's take a look at the first one. You see that we have two CH3CH2 groups. Go back. Again, the left hand strikes again, right? Where was I? We have two CH3CH2 groups. And then we have a CH group next to it. So where I'm going to start is with this CH, okay? So I'm going to move it over here just to make sure I don't run out of space, but I'm going to put the CH like this. And then I have two CH3CH2s attached to it. So I'm going to do CH2 like this, and then a CH3 like this. Then I have another CH2, oops. Starting to condense things already, Mr. Dion. Not good. Okay, so now I've covered those two. Now I've got CH2 and another CH2. So I'm going to put those attached to the carbon in red. So I'll put a CH2 and another one, CH2, like that. And then I have my OH tacked on the end. So I'll put OH. Could anybody tell me what's missing on my oxygen? If this is a proper Lewis structure, there's something missing from it. Lone pairs. Thanks, Vanessa. Yeah, friends. You know what my students used to have a saying, friends don't let friends leave lone pairs out, right? Anyhow, so there you go. So there's a Lewis structure from that condensed structure. So if I look at the next one, you can see that I have a carbon, one carbon that is bound to 3 CH2 CH3s, and then I have an OH attached to that one. So I'll start with the carbon in red, and I'll just kind of put this maybe here. Okay, so now I have 3 CH2 CH3. So I'll put a CH2, CH3. Here's the second one. I want to make sure I don't run out of space. And then I have this one here. There we go. And then I have my hydroxyl group, which is over here. There we go. So there's another Lewis structure from a condensed structure. Give me a thumbs up if you're on board with this. You say, yeah, I think I could do that. I could recognize a Lewis structure. I could draw a Lewis structure from a condensed structure. Okay. Now, of course, if you need more practice on this, where would you go? You'd go to the suggested practice problems and the textbook, and there's a whole plethora of problems you could try in there. Now, take a look at this molecule here. This is amoxicillin. Okay, very inexpensive compound. I actually looked it up one time. I made a note of it. It says cost between 2 and 5 cents per pill. I got to scribble that down here. Cost somewhere between 2 to 5 cents per pill. Okay, so amoxicillin is a very inexpensive antibacterial that's used to treat many different bacterial infections. It's one of the most commonly prescribed antibiotics in children. Anyhow, it belongs to a class of compounds called beta-lactams. And the beta-lactam portion of the molecule is shown right here. Don't worry, I'm not going to test you on what is a beta-lactam or anything. But if you're interested, it's just a type of compound. Anyhow, let's. It serves as the core for. It serves as a core structure for several antibiotics. Anyhow, that's neither here nor there. But you see how this is a Lewis structure of amoxicillin, a very commonly prescribed medication. Would you want to draw the structure of this out all the time? I certainly wouldn't. I mean, look at this thing. It's humongous. There's so many carbons, so many hydrogens. And, you know, another thing about this structure is it's very difficult to zoom in. You know, there's a hydroxyl here, but it's very difficult to train your eye to recognize it, to see it, right? You have to kind of dig in to say, oh, there's a sulfur here, there's a nitrogen here, et cetera, et cetera. So Lewis structures, practical for small molecules, not practical for a big molecule like amoxicillin, not very useful for that. So what we're going to learn to do now is we're going to learn to take that Lewis structure and convert it into something that we call a skeletal or a bond line structure. Now, I grew up calling it a bond line structure. I cut my teeth on that, so that's what I'll use. But again, skeletal structure is acceptable as well. Now, a couple of things about the bond line structure. It takes a lot less time to draw in the Lewis structure. You can draw it much, much faster, maybe in a tenth of the time, probably. So it takes much less time. And another thing is it helps train your eye or focus your eye in on what we call functional groups. Now, we're going to go over the functional groups soon, but I'll just say we have one here, we have one here, we have one here, there's another one here, there's another one here, and there's another one here. So you notice how in the Lewis structure, your eye doesn't get trained in on those. But in this one, in the bond line structure, your eye is trained in on these heteroatoms. When I say the word heteroatom, so heteroatom, it means an atom that is not carbon or hydrogen. That's all it means in organic chemistry. A heteroatom is nitrogen, oxygen, sulfur, right? Okay, atoms that aren't carbon or hydrogen. So with that in mind, bond line structures are the benchmark representations, okay? They are fundamental, Okay, they are the benchmark representations for organic compounds. It is critical to know how to draw these structures and without difficulty in order to succeed in an organic chemistry course. I'm not, these are actually the words of David Klein. I'm not putting them up here to be crude or to sound mean or anything like that, but you have to master bond line structures. There can be no question in your mind about them in order to be successful in organic chemistry. So let's go over the rules for bond line structures. Again, in our version of the textbook, this I think is covered in chapter 1.6, okay? Chapter 1.6 covers the bond line structures, but I'm showing you in here. So how do you read a bond line structure? Well, you probably notice some of these zigzags and lines, okay? The first thing is that the corner or an endpoint represents a carbon atom. So if we take a look at this first structure here, you see it says the endpoint or a corner. So there's a corner or an angle here, here, and here, right? Where two lines bisect or where three lines bisect, where there's a corner or an angle or an endpoint represents a carbon, okay? So it says here, there are 6 carbons in hexane, there are 4 in 2-butene and 2 in 2-butyne. So it says a corner or an endpoint. Well, if we take a look at this second structure here, here are the endpoints. There's one here and there's one here. And then we have 2 angles or corners, right? There's one here and there's one here. Now with the last structure, it's a little bit trickier, but you guys know about hybridization and that here, if there's a carbon atom here, what must be the hybridization of this carbon? It's not a trick question. It's attached to a single bond and a triple bond. So it's got a steric number of 2. So could anybody tell me what is the hybridization of carbon 2 and 3 based off of what we learned in chapter 1? It's sp hybridized, isn't it? Exactly. So this is an sp hybridized carbon here and here. But what do we know about the molecular geometry of sp hybridized carbons? The molecular geometry is linear. This bond angle is 180 degrees. And so when we transition from a single to a triple bond, we don't put an angle, okay? We just put a space in between, and we know as chemists that there is a carbon in there. Now, of course, at the end point, there is also a carbon here and here. So now, what else do we know about these bond line structures? Well, let's go back to the first one. The question that I asked you earlier today was how many bonds does carbon have when it's neutrally charged? Anybody? Let's just rehash this. How many bonds does carbon have when it's neutral? It's 4, isn't it? Exactly. So if I zoom in on carbon number 1 right here, it has 1 bond attached to it right now. So what bond line structures imply is the bonds that we don't draw are the bonds to hydrogen. So there's 1 bond drawn to this carbon right now. It's this one right here. It's not very pretty, but anyhow, there's 1 bond drawn to that carbon. So it's implied that there are 3 other bonds to hydrogen. We just don't draw them, but there's 1, 2, 3 here. Now, if I look at carbon number 2, how many bonds are missing from it? How many bonds are missing from carbon 2? 2, exactly. There's 2 that are shown, but there's 2 that are missing. So we assume that the 2 bonds that are missing are bonds to hydrogen. So there's 2 missing here, 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 and then on this carbon, there must be 3 missing, like that. So that is what a bond line structure represents. But if I just show you quickly me drawing the bond line structure of this molecule, which has 6 carbons, when my pencil touches the paper, okay, you see that black dot that I made? That's your carbon number 1. So your pencil touches the paper, 1, 2, 3, 4, 5, 6, done. So you see how much faster it is to draw the bond line structure of hexane, this molecule, than it would be to draw all those carbons and all of those hydrogens? Very time consuming. Okay, let's try the next one. How many hydrogens are missing from carbon number 1 in blue? This one here. 3, exactly. 1, 2, 3. And there's 3 missing from this one as well. 1, 2, 3. How many hydrogens are missing from carbon number 2?
2.
So how many bonds are on that carbon right now? There's 3 bonds on it, correct? Right, exactly. There's 3 bonds, so then it means it's missing 1. Okay? It's missing 1, as does carbon 3, right? Because it already has 1, 2, 3 bonds. Carbon can only have 4 bonds. So it's missing only 1 hydrogen. Does that help? Does that clear that up a little bit? I hope so. Okay. All right. And then for the last one, the 2 terminal carbons or the endpoint carbons, they both are missing 3 hydrogens. This guy is, this guy is, this guy is, this guy is. But if I highlight this carbon in yellow, how many hydrogens are missing from it? None. Exactly. There's no hydrogens missing. Why? It already has 4 bonds. There you go. So that's how bond line structures work. So why do we draw them like Charlie Brown's shirt? Why do we draw them like zigzags? Like There's a good reason for that. It's because if you were to make a molecular model of these compounds, they do actually adopt a zigzag conformation or shape because it minimizes repulsion within the molecule. So there's a reason why we draw the zigzag when we have sp2 and sp3 hybridized carbons. Okay, we draw a zigzag. However, if we have sp hybridized carbons, in that case, we use a linear geometry because the bond angle would be 180 degrees. Again, the carbon atoms are not labeled, but a carbon atom is assumed at every corner or endpoint along the zigzag. Now, if you read the textbook, one thing that he says, do not do this, and I'm going to tell you, do not do this. Okay, if you draw a molecule like this, you don't say, I'll just put carbons in here just so I remember, and then leave it like that. Okay, you either do all or nothing. You either draw a proper Lewis structure or a proper bond line structure. What I have drawn here, this is nothing. Okay, this is nothing. You're like, yeah, but it helps. Sorry, it's nothing. That is not a proper Lewis structure, and that is not a proper bond line structure. Okay, it is improper. So we don't draw hybrids somewhere in between the two. We follow the rules. We do one or the other. All right, so now it says you've got to be able to read bond line structures and use them to interpret the number of hydrogens in a molecule. So if I take a look at this molecule here, again, you don't have to worry about the names yet, but this molecule is called 2-pentanone. 2-pentanone. You can see that this carbon that is highlighted in green, okay, it is attached. It's got 2 bonds, so it's implied that there are 2 hydrogens attached to it. Give me a thumbs up if you're with me on that. Everybody with me on that? Okay, so then hopefully you can see that on this carbon, the one I have the blue circle on, there are no hydrogens on it because it already has 4 bonds. And so something that you need to practice is going from a bond line structure to a Lewis structure and drawing hydrogens in, okay, so that you're able to assess a bond line structure. All right, so let's see if we can identify the location and number of carbons and hydrogens in a structure. So I'm not going to do all of these. Let's just pick a couple of them. Could anybody tell me how many carbons are there in this structure that I have in the yellow circle? How many carbons are in there?
6.
There's 6, exactly, right? So if we draw a carbon at every endpoint, 1, 2, 3, 4, and then where there's an angle, 5, 6, okay? Could anybody tell me how many hydrogens are in here? Might take you a second longer to tally them all up. Yes, there's 14, exactly, right? Because we have CH3, 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 this is a CH, and this is a CH. So there's a total of 14. All right, so I'm going to assume that you can do the 2 that are to the left of that. Let's try something a little more complex. Now, this might take you a second to tally all of these up, but if I give you a second to think about it, could anybody tell me how many carbons are in this molecule? I haven't calculated it either, so I'll tally them up. Anybody get the number of carbons for this guy? Yeah, I got 15 as well. Okay, so I got 15 carbons. Okay, so let's write them all in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So there are 15 carbons in this compound, C15. We're not going to worry about the whole molecular formula, but now we should, or you should be able to draw in all the hydrogens on these. So I'm just going to pick and choose a couple of them. But if I was to give you this one here, how many hydrogens are missing from this one with the red circle? There's 1, exactly. Exactly, there's 1 missing from here. All right, heteroatoms are explicitly drawn. They're always shown, okay? So right? Heteroatoms are always explicitly drawn. They're never condensed. So what about if I was to give you this carbon here with this red circle on it? Could anybody tell me how many hydrogens are missing from it? From this guy? 0, exactly. It's already got 4 bonds. So what you need to be able to do is kind of go around and say, well, I'm missing 2 hydrogens here, 0 here, 0 here, 0 here. I'm missing 3 here, right? I'm missing none here, none here, none here, none here. I'm missing 3 here. I'm missing 2 here, missing none here, and then 3 here, and 3 here. All right, so then you can kind of just go around and fill in all the, oh, I'm missing one. There we go. This guy's missing one. Now I think I'm good. All right, so you need to practice putting in the hydrogens. All right, there we go. It might be tedious, but it's necessary in order to master the content. All right, so if you're given a Lewis structure or a condensed structure, you must also be able to draw the corresponding bond line structure. So I'm not sure if it's exactly page 54 anymore. It might be a different page, but you just follow the rules. So again, if your carbons are sp2 or sp3 hybridized, you follow the zigzag. So you see that we have 4 carbons in a row. So we have 1, 2, 3, 4. So the way you draw it, remember, when your pencil touches the paper, that's carbon number 1. We have 1, 2, 3, 4. Sometimes students will ask me, can you draw it like this? 1, 2, 3, 4. Sure, they're identical. There's nothing wrong with either of these. If you have an sp2 hybridized carbon, like this one here, remember the molecular geometry of an sp2 hybridized carbon is trigonal what? Trigonal planar, okay, where the bond angle would be 120 degrees. So you want to get the bonds as far apart as possible to get a bond angle of 120 degrees. This would be incorrect. When you're drawing single bonds, the direction of the bond is not relevant because you know you have free rotation around any sigma bond. So both of these structures are identical to each other. Heteroatoms are always drawn explicitly, and any hydrogens that are attached to them, those are also drawn explicitly as well. And this one here, the cardinal rule, never draw more than 4 bonds to a carbon atom. I'm not even going to do it because I feel like I'd have to take a shower or something after, okay? So you don't exceed the octet rule. So never draw more than 4 bonds to a carbon atom. If you do that, we call it a Texas carbon, okay? It's a big no-no drawing 5 bonds to a carbon. It doesn't exist. All right. So there you go. So that's a little bit about bond line structures. Now let's move on to identifying functional groups. So what is a functional group? All right, a functional group is a characteristic group of atoms and bonds that possess a predictable chemical behavior. Oh boy, I like the sound of this. So what that means is that us as organic chemists, when we look at a molecule, we can predict oftentimes how the molecule is going to react if we know our functional groups. We can say, well, here's an alcohol. An alcohol is going to react in this fashion. Here we have a carboxylic acid. We know that carboxylic acids react in this fashion. And so you can imagine that for somebody who's, pursuing a career in medicine, that somebody like a pharmacist or a doctor, they absolutely have to be able to look at a molecule and say, this is what's going to happen with this molecule when it reaches the stomach, which is a pH of 2, or when it reaches the large intestine, which is a pH of 11 or something like that. So when it comes to the functional groups, you have to memorize them. There is no magic bullet that I can give you about functional groups. You have to memorize them, and you need to know them very, very well. If you looked at our schedule, you probably saw that after chapter 4, I think we move up to chapter 14. So we tackle a couple of chapters about spectroscopy and spectrometry. You have to know the functional groups. There can be no question in your mind, oh, is this an aldehyde or a ketone? You have to know them frontwards, backwards, upside down, whatever. Anyhow, you have to know them. So let's go through them. Will you know them after listening to me talk through them for the next 10 minutes? No, absolutely not. You will have to practice it over and over and over and over and over and over in order to master functional groups. So let's see. Let's start with the top of the table here. So notice that the table in the textbook is a little bit different than this one, but it's pretty much the exact same thing, okay? Yes, you can never get enough repetition on functional groups. So if you have a triple bond between 2 carbons, we call that an alkyne, okay? It takes alkynes to make a world. So if you have a triple bond between two carbons, we call that an alkyne. The examples that they put in here, like 1-butyne, you don't even learn how to name that until chapter 9. So don't worry about the nomenclature of the compound. Just worry about identifying the functional group. Okay, triple bond between two carbons is an alkyne. Now, if you're wondering, hey, Mr. Dion, this compound that we looked at a few minutes ago, or was it this compound here? Would this be an alkyne? Yes, that is an alkyne. Okay, so let's go back here. If you say, Mr. Dion, was this an alkyne? Yes. Triple bond between two carbons. Anyhow, I digress. I can't keep doing that. Okay, so now if we have an oxygen bound to a hydrogen, okay, we call that an alcohol. So you find that in things like ethanol and isopropyl alcohol, rubbing alcohol, etc. So an OH group is an alcohol. Even if you look at cholesterol, okay, it has a hydroxyl group in it. The next one, okay, if you're wondering what the hell is this R thing, there's no R element in the periodic table. Well, let me cover what that is. Okay, it's here at the bottom. R refers to the remainder of the compound, and it's usually some group that consists of carbons and hydrogens. So all it means is another part of the molecule that's made out of carbon and hydrogen only, okay? So if we have a carbon-based group that's attached to an OH group, we call that an alcohol. If we have an oxygen between two carbon-based groups, we call that an ether. We've seen some ethers today, right? We saw one the other day when we were talking about constitutional isomers. Let's say you have CH3OCH3. Well, this oxygen in the middle is attached to this carbon and this carbon. So that means it is an ether. Okay, another example would be diethyl ether. So an oxygen between two carbons is an ether. The next one, if you understand what an alcohol is, you have an OH group. If you replace the oxygen with a sulfur, that's called a thiol. Okay, SH group is a thiol. There's also an old name for these. Sometimes they're called mercaptans, but don't worry about that. A sulfide. So if you have, just like an ether, if you have an oxygen between two carbons, we call that an ether. If you have a sulfur between two carbon-based groups, we call that a sulfide. Okay, so you have a thiol, which is SH, a sulfur between two carbons, that's a sulfide. The next one, very, I wouldn't say easy. Easy doesn't really belong in organic chemistry, but one of the most recognizable of the functional groups is an aromatic. So if you have 6 carbons in a ring, each one is sp2 hybridized. They each have 1 hydrogen attached to it. That's called an aromatic or an arene. So sometimes I'll call it aromatic, sometimes I'll call it arene, sometimes I might even call it aryl. Okay, let me use a finer tip pen here. Sometimes I might call it an aryl group. They all mean the exact same thing. One thing you'll learn about organic chemistry is organic chemists love different ways of describing the same thing. What else here? The next one is a carboxylic acid. So before we get into the carboxylic acid, acyl halide, anhydride, ester, and amide, you notice that every single one of these has a carbon with a double bond to oxygen. Okay, they all contain a carbon with a double bond to oxygen. If you have a carbon with a double bond to oxygen, we have a name for that. Okay, let me scribble it down here. If you have a carbon with a double bond to oxygen, we call that a carbonyl. Okay, it comes up a few times in organic chemistry, but we call that a carbonyl. So if you have a carbonyl that has an OH group attached to it directly, that's a carboxylic acid. Okay, now you might be saying, well, what's the difference between a carboxylic acid and an alcohol? Well, the OH group here doesn't have a carbon with a double bond to oxygen before it, preceding it. So there's a big difference between a carboxylic acid and an alcohol. If you have a carbonyl followed up by a halogen, where X is equal to chlorine or bromine, you don't really see this with iodine or fluorine, but we call those acyl halides, okay? So an acyl halide. So this is acetyl chloride, which is a pretty interesting compound. The next one is if you have 2 carbonyls with an oxygen in the middle, an sp3 hybridized oxygen in the middle, that's called an anhydride. Okay, so an anhydride. The next one is an ester. And sometimes students will get ester and carboxylic acid mixed up. But in a carboxylic acid, we have the carbonyl and then an OH group. Whereas in an ester, we have a carbonyl, yes, but then we have an oxygen attached to a carbon-based group, okay, not a hydrogen. So we could put here not H, okay? That's an ester. The next one is an amide. If you've studied peptides and proteins, you've probably seen amides in those because peptides are held together by amide bonds. Anyhow, in an amide, we have a carbonyl followed up by a nitrogen, okay, and the nitrogen. has two R groups. The R groups can be, we'll put here, can be carbon or hydrogen based. Okay, so you see here we have two hydrogens. We call that a primary amide. If there's one hydrogen and one R group, we call it a secondary amide. If it's got two R groups, then we call it a tertiary amide. The next one is an amine. We have a nitrogen attached to R groups, and these R groups can be, can be hydrogen, or I'll just put it the same way it was before, carbon-based groups or hydrogen. Then we call that an amine. If it's only got one hydrogen, then it's a secondary amine. If it's got no hydrogens, it's a tertiary amine. If it has two hydrogens, it's a primary amine. I'll cover that in more detail later on. And then I have a couple of stragglers over here. If you have a double bond between two carbons, that's called an alkene. So triple bond is an alkyne, right? Triple bond was an alkyne. Okay, a double bond is an alkene. If you have a carbonyl that's flanked by two carbon-based groups, that's called a ketone. And so this one here, we have two R groups, that's called a ketone, not ketone. Okay, that's not anything. It's ketone. And the last one is if you have a carbonyl that's flanked by a carbon-based group on one side, and you have to have a hydrogen on the other side, that's called an aldehyde. Okay, so if your carbonyl has a hydrogen directly attached to the sp2 hybridized carbon, in that case, you're dealing with an aldehyde. There you go. So those are all the functional groups that you are responsible for in this class. I'd add one more that shows up a little bit in this class, and that is a nitro group. So if you have RNO2 like this, we call that a nitro group. Let me just see here. Yeah, a nitro. So I'll put here nitro group. And the nitro group actually has a really interesting Lewis structure. So I'll just draw the Lewis structure here because it's got two charges. Maybe I can draw it prettier than that. Two charges that cancel each other out. Check this out. So you've got a double bond to this oxygen, and then you have a single bond to this oxygen. So this oxygen has a negative charge, and the nitrogen has a positive charge. They balance each other out. +1 and -1 give you what? 0. So there's a nitro group. Anyhow, so now we're getting into formal charges. You need to be able to recognize formal charges in a compound. But before we do that, what I think we will do is we will get out of here for a second. We'll go over to a Taylor Swift blank space here, and I'm going to draw a compound. Okay, just bear with me. Try to draw neatly. Okay, so I'm going to give you some time. I'm going to draw a second compound, but see if you can identify the functional groups in this compound. Not my best artwork, so I'll fix this a little bit. I'm going to draw a second compound down here in blue. All right. Okay, in the compound in blue, the compound in black, does anybody recognize any of the functional groups in here? Yeah, exactly. So you're close. Yeah, so there's one that's off. So, okay, let's pick one of them. We'll pick a thiol. Yes, there's definitely a thiol in here. Yeah, so the SH, right? You have a carbon here, and then you have SH attached to it. So this would be a thiol. Yeah. Any others? Yeah, there's an ester in there. Absolutely. Right. We have an ester right here. Right, because this is a carbon and this is a carbon. So this is an ester. And I saw somebody had written ether. So we have a carbon here and a carbon here. So we have a carbon, two carbons with an oxygen in the middle. So that would be an ether. Okay, there's one other in here. Does anybody recognize another one? It's not aromatic. There's one other functional group. So this one here, this would be an alkene. Okay, so this is an alkene. Okay, don't get mixed up between aromatic is when you have a 6-membered ring with 3 double bonds, okay? If I have a 6-membered ring, that's cyclohexane, okay? So that's an alkane. And if I just put 1 double bond, that's not aromatic, okay? This is aromatic, and this is just an alkene. All right, good. There we go. What about the one in blue? Maybe we could just, yeah. Does anybody recognize any of the functional groups in the one in blue? Yeah, there's definitely an alkene in it. Yeah, absolutely. There's an alkene right here. So we'll put alkene. Any others? An amine, yeah. So this is an amine here. So this is an amine. Yeah, there's 2 more. There's an alcohol, yeah. There's an alcohol here. Yeah, alcohol. And then here we have a ketone, right? Yeah, so we have a ketone, ketone. Here, so you want to practice identifying your functional groups, okay? So if you go into practice problems, there are several practice problems where he covers functional groups and gives you some practice in identifying this functional group and that functional group. All right, so now we've covered bond line structures, we've covered functional groups. Let's take a minute and talk about formal charges. Now, if you remember last class, I went over my formula for calculating formal charges. And I said that formal charge was equal to the number of valence electrons, subtract the number of sticks. I'll just, what do I have parentheses for? I'll just put subtract the number of sticks, subtract the number of dots. Okay, so let's say we have this carbon here. How do we know that has a negative charge? Let's go over it one more time. Could anybody tell me how many valence electrons does carbon have? 4, exactly. So we have 4 minus 3 sticks minus 2 dots, which gives us -1. Okay, so that's why we have a -1 charge on this carbon. Okay, so now it says a carbon will have 4 bonds when it does not have a formal charge. Okay, that's good. We know that. When a carbon has a positive charge, we call that a carbocation. Okay, now a carbocation is going to have a total of 3 bonds, and it's going to have an empty orbital. So that means a carbocation is sp2 and is trigonoplanar. So if you have a bond line structure, in order for you to know that it's a carbocation, somebody has to put the positive charge there on it for you. But if I take a look at this carbon, which has the positive charge, how many hydrogens are missing? Well, it says here there's no hydrogen atoms, because what did we say? When we have a carbocation, it has 3 bonds, okay? And its molecular geometry, I'll remind you, is trigonal, what? Planar. It is flat as a pancake, okay? So now if I take a look at this carbocation, that carbocation has 1 hydrogen attached to it, doesn't it? How do we know that? Because a carbocation has 3 bonds. There's 2 that are drawn in the bond line structure, but there's 1 that's not shown, and that's the bond to hydrogen. And then if we look at this last carbocation, there's only 1 bond drawn to it, but you guys know from the rule that when we have a carbocation, there's 3 bonds, there's 2 that aren't drawn, so those must be bonds to hydrogens. Give me a thumbs up if you're with me on that idea. You see a positive charge, you know there's a total of 3 bonds. Okay, so you can fill in the missing hydrogens. Now, if we have a carbanion, the carbanion has a negative charge. Okay, carbanions have a steric number of not 3, but 4. And so carbanions are sp3 hybridized, okay? But they have a lone pair, so you have 3 bonds and a lone pair. Well, if you do enough practice problems, by the time you get to the end of all the practice problems in chapter 2, you will need very little guidance with this. You'll actually kind of recognize it really quickly when we have formal charges. So formal charges affects what? It affects stability. It affects reactivity. So you've got to be able to identify formal charges in compounds. Now, we have this interesting compound shown down here, and it's missing its formal charges. So what I'd like to do is give you I don't know, 40 seconds or something. I'll time it. And I'd like you guys to try and identify the formal charges in this compound. I'll give you 40 seconds to give that the old college try. I'll even set my iPhone timer here. Okay, time's up. All right. Let's see. Did anybody identify any formal charges? What I'll do is I'll highlight some of the atoms and you can tell me if you found a formal charge or not. So what if I highlighted this oxygen in yellow? Okay. Anybody identify a formal charge on this guy? Be +1, wouldn't it? Okay. So this one would be +1. Exactly. So if I just go over it out loud, so oxygen has 6 valence electrons minus 3 sticks and 2 dots, gives you +1. Let's see. What about the sulfur? Does it have a charge? Does the sulfur have a charge? So it's going to have a charge of 0. So the sulfur has no charge. So sulfur has 6 valence electrons minus 4 sticks and 2 dots, which gives you 0. So there's no charge on the sulfur. What about this oxygen? If I highlight this oxygen in blue, is there any formal charge on that oxygen? On the oxygen in blue. Yeah, it's going to be -1, isn't it? Right? It's going to be -1. Okay. So if we go over that, you get 6 minus 6 dots, 1 stick. So that gives you -1. Yep. And then what about this nitrogen here in the red circle? Any charge on it? +1. Exactly. So we have 5 minus 4 sticks, 0 dots, gives you +1. There's no other formal charges in the molecule. So overall, this molecule has a charge of, or I guess it's an ion, has a charge of +1. So there you go. You've got to be able to identify formal charges. So, sometimes students will ask me, do you have a shortcut or do you have a summary of all this or something? Well, the whole class is a summary of the subject, I would say. But, you need to identify bonding patterns, I would say, for oxygen, nitrogen, and carbon. So this first slide has all the bonding patterns for oxygen. The next one has the bonding patterns for nitrogen. And the one after that, well, we've already covered carbon, so I guess oxygen and nitrogen is where we're going to start. Or I guess it's where we're going to finish up because we've already done carbon. Anyhow, so if oxygen has 1 bond and 3 lone pairs, it has a charge of -1. You can see that right here, okay? 1 bond, 3 lone pairs. So if we see an oxygen in a bond line structure and it just has a negative charge, it's implied. You have to know as an organic chemist that there are 3 lone pairs missing, okay? If the oxygen is neutral, you guys know that oxygen, when it's neutral, has 2 bonds and 2 lone pairs. So in this bond line structure here, it's implied that there are 2 lone pairs. Finally, when oxygen has 3 bonds and 1 lone pair, it's positively charged. So again, it's implied that there is 1 lone pair on this oxygen. Now, if we think about nitrogen, when nitrogen has 2 bonds and 2 lone pairs, it has a negative charge. So again, it's implied that there's 2 lone pairs here. You have to be able to fill that in. When oxygen has 3 bonds and 1 lone pair, it's neutral. So it's implied that there's a lone pair here. And then finally, when oxygen, or sorry, did I say oxygen when I meant nitrogen? When nitrogen has 4 bonds and no lone pairs, it has a charge of +1. Now, I can tell you that if you practice enough, you won't need to think about this at all. Every time you see an oxygen with 3 bonds and 1 lone pair, you'll just say +1 charge, and you won't worry about it. Every time you see a nitrogen with 2 bonds and 2 lone pairs, you'll say it's a negative charge. You won't have to think about it very much. But to get you started, this is a good starting point. And remember, the formula was formal charge is equal to the number of valence electrons, subtract the number of sticks, subtract the number of dots. Okay, that's a formula I went over with you in the last class. So With that in mind, let's see if we can fill in the lone pairs on the oxygen atoms here. So in E, how many lone pairs are missing in E on the oxygen? Anybody? It's got a negative charge on the oxygen. Exactly. It's missing 3 lone pairs. So we'll put those in there. 1, 2, 3. The oxygen in F is neutral. It's got 2 bonds. Therefore, it's missing how many lone pairs? 2. Exactly. So we'll pencil those in. And then finally, the last oxygen has a +1 charge. So it's missing how many lone pairs? Great. It's missing 1. There you go, my friends. That's all there is to it. Fill in the missing lone pairs.